Good morning, everybody. Today I want to go over the review sheet as we are going to be taking a test on the energy topic. So on Friday you were supposed to do the energy review. I'm going to quickly run through this, hopefully quickly, and hopefully it should clear up any confusion you might have, and this should really prepare you well for your test tomorrow. So looking at number one, I think this is repetitive at this point, but which color of the visible spectrum has the shortest wavelength? Whenever we're talking about electromagnetic energy and wavelengths, we know we go here to page 14 of the reference table. And looking at page 14 of the reference table, they're talking about which color has the longest and shortest wavelength. And you could see again, all these different energies are different by their wavelengths. So as we go to the left, decreasing, the shortest would be on the left, and increasing is the other way to the right. And when we skip down to visible light, it is broken up into colors and it works the same way as the rest of the chart. So the shortest wavelength would be on the left. That would be violet. Choice A for number one. Number two, which type of electromagnetic energy has the longest wavelength? And they give you UV, X-ray, what else did they give us? Radio waves and infrared. So pretty simple. All the way to the right would be the longest wavelength, and that would be radio waves all the way to the right because increasing to the right. Number three, a surface will most effectively reflect insolation if it is. So remember, insolation is energy coming down from the sun, it's heat, and always think, what are we told to wear on a very hot day? In the summer, we're told to wear light colors. So already I know in number three, I could eliminate for reflecting energy, I could eliminate C, I could eliminate D. I'm left with A and B, so we're down to the textures. And I don't know if you remember, but I said that the best reflector on Earth is a snow-covered field, maybe a glacier, something like ice. And just think about it, that would be a smooth texture. So we're looking at two things for the best reflectors. Texture should be smooth, and color should be light for a good reflector. If you want a good absorber, you want the exact opposite. You'd want a rough and dark colored. Actually, that's what you would want on the surface there for a good absorber. But they were looking for a reflector. So choice B is your choice for number three. Number four, I already mentioned it just now, under identical conditions, which surface will reflect the greatest amount of insolation? That would be a glacial ice sheet. It's light color and smooth texture. Now, if they ask for the best absorber, I did tell you guys a forest is the best absorber because it's dark color and a rough texture. Number five is a key thing you need to know. Anything that absorbs energy or heat well, a good absorber is a good radiator. Choice C for number five. Number six, the diagram below shows temperature values at various points in a solid piece of aluminum. Toward which point will heat flow from point P? So if you take a look at point P, it's 10 degrees Celsius. And remember what we said, all energy will flow from high to low. So if this is 10 degrees Celsius, the energy will only flow to another point that is a lower temperature, high to low. And the only one, look at D, same temperature. C is higher than that. That's not going to work. B is the same temperature, but A is a lower temperature. So from P, energy will flow from high to low. For this, you should have gotten choice A. Let's go to number seven. Turn the page, if I could turn the page. Number seven, which diagram best represents heat transfer, mainly by the process of conduction? Conduction. Now you just gotta need to know this but conduction is heat transfer through a solid. All right, so if you take a look here, this is going through air. In fact, this looks like a convection current, so choice A would be convection. Choice B is the sun's energy traveling through Earth, or to Earth. That's traveling through space. Any energy that travels through space is electromagnetic, and that's exactly what we talked about on page 14 of the reference table. But take a look at C. C has atoms in a metal rod vibrating. Well, that metal rod's solid. The atoms are in a solid, and conduction occurs in a solid. So choice C is a solid choice. Oh, bad joke. Mark that down, people. And by the way, the asthenosphere, take a look. Those are convection currents. We talked about that again when we talked about our tectonic plates. Let's go to number 8. The diagram below represents a large beaker of water being heated to demonstrate convection. Notice where the flame is. The flame is in the middle. Whenever it's in the middle, you get two convection currents, right? Because when you heat something up, whether it's water or air, heat rises. So you can see it rising in the middle, and then it's cooler over here. It travels to the sides, and you get your two convection currents when the burner is in the middle of the beaker. So the movement of water upward from A toward B, why is that happening? Just think of a gas or anything hot. Hot air rises because it's less dense. Convection is all about differences in density. Know that. Let's go to the next page. Number 9. We go to number 9 on the top of the next page, and the diagram below represents a laboratory model used to demonstrate convection currents. They show a burning candle in a closed box with two open tubes at the top of the box. Which diagram correctly shows the airflow caused by the burning candle? Well, if you take a look, the candle is on the right side. So if it's on the right side, what it should be doing, the energy should be moving upward on the right side and then going out. As it goes out, it's cooler, it's more dense, it sinks in and comes back around. You should only have one convection current here, by the way. This one is 2. That would only be if the heat was in the middle, and that wouldn't even work because the air is moving down there. So we're looking for the picture where on the right, where the heat is, you want rising motion. I want you guys to take a close look at choice D. See the burning candle? You could see the air going upward. As it goes out, it cools down, sinks into the other tube, and comes back around, and this is your convection current. Remember, whatever side that candle is on, that's where you're going to get the rising motion because of less density. So, if it's in the middle, you'll get two convection currents, but this is on the right-hand side. Let's go to so that's D for number 9. Number 10, which method of energy transfer is primarily responsible for energy being lost from Earth into space? We're looking for the energy that's moving through space or air. That would be radiation, choice D. Number 11, remember when we talked about potential versus kinetic energy? Which energy transformation occurs as a rock falls freely from the top of a vertical cliff? In other words, here's your cliff, here's your rock, it's going to fall down toward Earth. Well, that rock, remember, the higher you are above Earth's surface, the more potential energy you have. So starting from the top, there's a lot of potential, and if there's a lot of potential, there's very little kinetic. As the rock starts to move, kinetic energy will increase, and if kinetic energy goes up, potential energy goes down. Choice B for number 11. Number 12, a temperature of 20 degrees Celsius is equal to, so in order to do our temperature conversions, we got to go to this chart. And when I do go to this chart, remember Celsius is in the middle. So there's Celsius in the middle. I'm going to go to 20 degrees Celsius. I got to slide down, slide down. There we go. If I slide over, remember Fahrenheit goes up 2 degrees per line. So if I slide over, 20 degrees Celsius is 68 Fahrenheit. Or it would be 293 Kelvin. So we're looking for the choice that either says 68 Fahrenheit or 293 Kelvin. Let's go and see. Oh, they tried to trick you. Look where they tried to trick you. They did put a 293, but that's Fahrenheit. We said in Fahrenheit, it's 68 degrees Fahrenheit. So for 12, you should have gotten C. For number 13, as I go there, trying to run through this relatively quickly. Now I could look at this chart and it talks about how much heat energy is needed to raise the temperature of 1 gram sample of 4 different materials. Which of these has the highest specific heat? Well, all I want you to remember is this. You could read this graph, you would actually be able to tell, but you don't need to. Because remember, specific heat is on page 1 of the reference table. And remember we marked it up, smallest specific heat is on the bottom, the largest specific heat is on the top, and that would be liquid water. Liquid water has the largest specific heat of any naturally occurring substance on Earth. What does that mean? That means that liquid water is the toughest material, natural material on Earth to change the temperature of. Again, remember what I told you. Think of a boiling pot of water. So liquid water has the highest specific heat of any naturally occurring substance on Earth. Let's go to number 14. During which phase change of water is the most energy released into the environment? When they start talking about phase changes, and they're talking about whether energy is gained or lost, what we're going to do, we're going to go to page 1 of the reference table, just under specific heat, and see which phase change is the most energy released into the environment. And they kind of make this easy for you. Look, heat energy gained, melting. So we're looking for heat energy to be released. Heat energy is released during freezing, and it's also released during condensation. They wanted to know which one has the most energy released. Well, you could kind of see condensation has a lot more energy released than freezing. So for this one, condensation should be the answer. Did they say condensation? Not exactly, but they did say water vapor condensing. Same thing. Number 15, the average temperature at Earth's equator is higher than the average temperature at Earth's south pole, because the south pole, remember what we talked about, insolation, incoming solar radiation. And remember we said that the most intense heat is at the equator. You have the North Pole up here, the South Pole down here, and here's the equator. And the equator gets hit most directly by the sun. It has the highest angle of insolation. They want to know, why does the South Pole get so much cooler? Why is it so cold there? And that's because it receives much less intense insolation. It gets those tangential rays, not perpendicular or overhead rays. So it receives less insolation, less intense insolation at the poles than you do at the equator. So 15 is A. Let's go to number 16. And number 16, we talked about angle of insolation versus intensity of insolation. And remember, I think they showed a picture, right? Now, they didn't have a person in the picture, but they had flashlights. Now, if this person has the sun directly overhead, the sun's rays are just going to beam right down on this person. And that is a direct hit. If you decrease the angle of insolation, let's say to here, maybe like a 30 degree, you're getting hit at like a sideways type of deal. This is much more intense when you get hit directly with the sun's rays. That would form a 90-degree angle with the horizon. And when you get that 90-degree angle, we call those direct rays, perpendicular rays, anything like that. So as the angle of insolation goes up, intensity goes up. That is a direct relationship. That would be choice B. Number 17. Which of the following Earth surfaces usually reflects the most incoming solar radiation? We already said that. Light color, smooth texture. This is going to reflect the most incoming solar radiation on Earth, a snow-covered field or a glacier. Next up, we're almost there. Number 18 and 19 is an awesome picture of this guy riding over a hill. I would imagine that's not so comfortable for this guy. He could hardly fit on his bike. But here's point A, here's point B, here's point C. At which point is potential energy the greatest? Remember, it is whenever you are highest above the surface of the Earth. That would be over here. That is choice B. For number 19, what happens to energy as this cyclist travels from point A to point C? So, as he goes from point A to point C, he's going higher above Earth. So, at this point, wouldn't potential energy be going up? So I'm just going to mark that down here. PE, potential energy goes up. Kinetic is going down. Now we hit our highest potential energy, and once you hit that, he's going to go downhill. At this point, kinetic energy would start to increase, and potential will decrease. So what happens to the energy as this guy travels from point A to point C? Which choice is correct? Look at choice A. Choice A says kinetic energy decreases, then increases. And that is the answer. Let's go to number 20 and number 21. And when we get to this, pretty simple. We are taking a look at the picture of Earth in its orbit around the Sun. And the instructions, remember when you get these group questions, you should definitely read the instructions. Base your answer to questions 20 and 21 on the diagram below, representing Earth's revolution around the Sun. Points A through D represent the dates for the change of seasons. Which date is represented by point A? Now you got to look closely. I always look at the northern hemisphere. That is where we live. And if you take a look at the northern hemisphere, you want to see, I always said, start with these 2 points, the ones that are in a straight line with the sun, A and C. You could see in A, the northern hemisphere is tilting away from the sun. That's away from the heat. So this would be December 21st here. And this point, point C, you could see the northern hemisphere is tilting to the sun, to the heat. That's June 21st. And then if you take a close look at the path, you can kind of see the arrow is pointing this way. So this is December, 6 months later June, in the middle is 3 months later. This would be March 21st. This would be September 23rd. So what date is represented by point A? Remember I told you guys always mark these first and the questions become super easy. So point A is quite clearly December 21st. So for this one, number 20, you should have gotten B. And then for number 21, which point represents the greatest intensity of insolation for the northern hemisphere? If we have a higher intensity, that means we have very hot weather. Hot weather occurs in the summer. That would be point C. So 21 is C. That covers the test for tomorrow. It's everything on the energy unit. If I were you guys, I would definitely look over this review sheet and probably keep it out because you can, in this case, you're home taking the test, and it will help you greatly. I wish you guys luck tomorrow, and I will leave more instructions about the test. Have a good day, and we'll touch base later.